This is one of my favorite examples about how physicists develop intuition. It goes to the work of Galileo. So, again, let's go back to Greek philosophers, or maybe Aristotle in this case. Now, again, let's make a criticism. He thought that objects, the heavier objects fall faster than the lighter objects.
Makes sense.
It kind of makes sense. And, people say about the feather and so on, but that's because of the air resistance. But you might think like if you have a heavy stone and a light pebble, the heavy one will fall first. If you don't, do any experiments, that's the first gut reaction. I would say everybody would say that's the natural thing. Galileo did not believe this, and he kind of did the experiment. Famously, it said he went on the top of Pisa Tower and he dropped, these heavy and light stones, and they fell at the same time when he dropped it at the same time from the same height. Okay, good. So he said, I'm done. I've showed that the heavy and lighter objects fall at the same time. I did the experiment. Scientists at that time did not accept it. Why was that? Because at that time, science was not just experimental. The experiment was not enough. They didn't think that they have to soil their hands in doing experiments to get to the reality. They said, why is it the case?
Why? Yes.
So Galileo had to come up with an explanation of why heavier and lighter objects fall at the same rate. This is the way he convinced them, using symmetry. He said, suppose you have 3 bricks, the same shape, the same size, same mass, everything. And we hold these 3 bricks at the same height and drop them. Which one will fall to the ground first? Everybody said, of course, we know that symmetry tells they're all the same shape, same size, same height. Of course, they fall at the same time. Yeah, we know that. Next. It's trivial. He said, okay, what if we move these bricks around with the same height? Does it change the time they hit the ground? They said, if it's the same height, again, by the symmetry principle, because the height translation, horizontal translation is the symmetry, no, it doesn't matter. They all fall at the same rate. Good. Does it matter how close I bring them together? No, it doesn't. Okay. Suppose I make the 2 bricks touch and then let them go. Do they fall at the same rate? Yes, they do. But then he said, well, the 2 bricks that touch are twice more mass than this other brick. Yeah. And you just agreed that they fall at the same rate. They say, yeah, we just agreed. That's right. That's strange. Yes. So he deconfused them by the symmetry reasoning. So this way of repackaging some intuition, a different intuition, when the intuitions clash, then you side on you replace the intuition.
That's brilliant. I in some of these more difficult physics ideas in the 20th century and the 21st century, it starts becoming more and more difficult to then replace the intuition. What does the world look like for an object traveling close to the speed of light? You start to think about like the edges of supermassive black holes, and you start to think like, what's that look like? Or I've been into gravitational waves recently. It's like when the fabric of space-time is being morphed by gravity. Like, what's that actually feel like? If I'm riding a gravitational wave, what's that feel like? I think some of those are more sort of hippie, not useful intuitions to have. But if you're an actual physicist or whatever the particular discipline is, I wonder if it's possible to meditate, to sort of escape through thinking, prolonged thinking and meditation on a world, like live in a visualized world that's not like our own, in order to understand a phenomena deeply. So like replace the intuition, like through rigorous meditation on the idea in order to conceive of it. I mean, if we talk about multiple dimensions, I wonder if there's a way to escape the 3-dimensional world in our mind in order to then start to reason about it. It's the more I talk to topologists, the more they seem to not operate at all in the visual space. They really trust the mathematics, which is really annoying to me, because topology and differential geometry feels like it has a lot of potential for beautiful pictures.
Yes, I think they do. Actually, I would not be able to do my research if I don't have an intuitive feel about geometry. Mm-hmm. And we'll get to it, as you mentioned before, that how, for example, in string theory, you deal with these extra dimensions. And I'll be very happy to describe how we do it, because without intuition, we will not get anywhere. And I don't think you can just rely on formalism. I don't. Mm-hmm. I don't think any physicist just relies on formalism. That's not physics. That's not understanding. So we have to intuit it. And that's crucial. And there are steps of doing it. And we learned it might not be trivial, but we learn how to do it. Similar to this Galileo picture I just told you, you have to build these gradually. But
you have to connect the bricks.
You have to connect the yeah, exactly. You have to connect the bricks, literally.
Yeah.
So then so going back to your question about the path of the history of the science. So I was saying about the electricity and magnetism and the special relativity, where simple idea led to special relativity. But then he went further, thinking about acceleration in the context of relativity, and he came up with general relativity, where he talked about, the fabric of space-time being curved and so forth, and matter affecting the curvature of the space and time. So this gradually became a connection between geometry and physics. Namely, he replaced Newton's, gravitational force with a very geometrical, beautiful picture. It's much more elegant than Newton's, but much more complicated mathematically. So when we say it's simpler, we mean in some form it's simpler, but not in pragmatic terms of equation solving. The equations are much harder to solve in Einstein's theory, and in fact, so much harder that Einstein himself couldn't solve many of the cases. He thought, for example, you couldn't solve the equation for a spherical symmetric matter, like if you had a symmetric sun. He didn't think you can actually solve his equation for that. And a year after he said that, it was solved by Schwarzschild. So it was that hard that he didn't think it's going to be that easy. So the formalism is hard. But the contrast between the special relativity and general relativity is very interesting, because one of them has almost trivial math, and the other one has super complicated math. Both are physically amazingly important. And so we have learned that, the physics may or may not require complicated math. We should not shy from using complicated math like Einstein did. Einstein wouldn't say, I'm not going to touch this math because it's too much, tensors or, curvature, and I don't like the four-dimensional space-time because I cannot see four dimensions. He wasn't doing that. He was willing to abstract from that because physics drove him in that direction. But his motivation was physics. Physics pushed him. Just like Newton pushed to develop calculus because physics pushed him, that he didn't have the tools. So he had to develop the tools to answer his physics questions. So his motivation was physics again. So to me, those are examples which show that math and physics have this symbiotic relationship, which kind of reinforce each other. Here I'm giving you examples of both of them, namely Newton's work led to development of mathematics, calculus. And in the case of Einstein, he didn't develop Riemannian geometry, he just used them. So it goes both ways. And in the context of modern physics, we see that again and again, it goes both ways.